This is real footage from November 7th, 1940. Nobody is driving. The bridge is moving on its own. 4 months earlier, the Tacoma Narrows Bridge had opened, engineered by experienced professionals, reviewed by federal authorities, built to the standards of its time. In a few minutes, it will tear itself apart, not in a storm, in a steady wind of 42 miles an hour. The popular explanation for what you're about to see is resonance, the wind matching the bridge's natural rhythm. That explanation is wrong. This is the real mechanism, and the rule it created that every suspension bridge still follows. The bridge crossing the Tacoma Narrows stretched 2,800 feet between its towers on a deck just 39 feet wide. Its original engineer, Clark Eldridge, planned a conventional deck, a deep, open truss, 25 feet tall, letting wind pass straight through. Federal authorities, reviewing the project, required a second engineer to check Eldridge's design. That engineer was Leon Moissafe, already well known for a theory that long, flexible suspension bridges didn't need that kind of heavy truss at all. The main cables alone, he argued, were stiff enough to absorb the wind's pressure. He replaced Eldridge's truss with a solid steel plate girder, only 8 feet deep. It also cut the projected cost by nearly a third, from around $11 million to $7 million. Relative to its length, that girder was roughly 350 times shallower than the bridge was long, proportions no suspension bridge had used before. Moissafe's theory accounted for wind as a steady sideways push. It did not account for what a solid, shallow deck does to moving air. When the bridge opened on July 1st, 1940, crowds crossed it in a procession of cars, flags flying, a genuine civic triumph, and at the time, the third longest suspension span on Earth. Almost immediately, the deck rippled in the wind, a slow, vertical up and down motion, sometimes several feet high. It started even before the bridge opened. Construction workers reportedly chewed lemons on the job to settle their stomachs, and nicknamed the bridge Galloping Gertie. Once it opened, that motion became a minor tourist attraction. Drivers came specifically to feel the bridge sway beneath them. For 4 months, that vertical rippling was the whole story. Then, on the morning of the collapse, a steel band clamping the main cable at mid-span slipped. One side of the deck was suddenly free to move independently of the other. The motion stopped rippling up and down, and started to twist. Here's the explanation most people already know. The wind matched the bridge's natural frequency, and the bridge resonated, like a swing pushed at exactly the right moment, over and over, until it swung wildly out of control. It's a clean explanation. It's taught in classrooms. It even appears in physics textbooks. There's just one problem. For that explanation to work, the wind itself needs to pulse, in rhythm, at the same rate the bridge is twisting. On November 7th, the wind wasn't pulsing. It was steady. The bridge's fatal twisting repeated about 12 times a minute, roughly once every 5 seconds. Wind blowing steadily past a girder, this shape naturally sheds small swirls of turbulence, over and over, many times faster than that, nowhere close to the bridge's own twisting rate. If the wind itself wasn't keeping that beat, something else was. The real answer is a feedback loop, and it has a name: aeroelastic flutter. Once the deck began to twist, even slightly, that twist changed the way air moved around it. The changed airflow pushed back with more twisting force than before. Each cycle fed the next. The bridge wasn't being driven by an outside beat. It was, in effect, driving itself. Picture the difference. An open truss lets wind pass through it, in gaps, with nothing solid to push against. A solid plate girder is different. Wind flowing over and under it behaves the way air behaves over a wing. It can generate lift, and it can generate torque. When this deck twisted even a little, its solid face caught the wind at a new angle. That new angle pushed harder in the same twisting direction. There was no natural point where the motion leveled off. Each swing grew larger than the one before it. What began as an unremarkable ripple became, within minutes, a twist steep enough to lift one edge of the roadway many feet above the other. By 11 that morning, the twisting had become violent enough to tear the deck apart. A 600-foot section broke free and fell into the water below. No person died. Leonard Coatsworth, the last driver on the bridge, abandoned his car, and crawled to safety on his hands and knees. His dog Tubby was left inside it. Professor Frederick Farquharson, who had already been testing this exact bridge in a wind tunnel for months before the collapse, reached the car and tried to free the dog himself. He was bitten for his trouble and had to retreat. Neither the car nor Tubby were ever recovered. A federal board of 3 engineers investigated and reported back the following March. One of them was Theodore von Karman, already famous for his work on the physics of swirling air, and by some accounts personally drawn to a theory centered on the kind of swirling vortices he'd spent his career studying. But the board's own official report was more cautious than that individual framing, on record calling reliance on that specific vortex explanation unlikely. The board's actual conclusion was broader. The bridge's flexibility was the principal cause. Its solid deck behaved aerodynamically like a wing, and aerodynamic forces on bridges were, in their own words, still poorly understood by the profession. It was Farquharson, the one who'd actually built and run the wind tunnel, not von Karman, who kept testing for years afterward. His full findings weren't published until 1949, almost a decade after the collapse. Even today, the precise mechanical details of exactly how the twisting took hold are still an active technical conversation among specialists. The feedback loop explanation you just saw is the accepted, evidence-backed account, confirmed as recently as a 2022 computer simulation. But it is fair to say the finest details were not settled overnight, and in the smallest particulars, still aren't. The lesson wasn't just to build it stronger. It was that nobody had been testing bridge decks the way aircraft wings were already being tested, for how they behave in moving air, not just how much weight they can hold. The replacement bridge, opened a decade later, used a stiffening truss 33 feet deep, 4 times deeper than the original, with open slots letting wind pass straight through the deck instead of pushing against it. Farquharson's team tested it first, in a wind tunnel, across roughly 200 configurations. It was fitted with hydraulic dampers, the first suspension bridge built with them. And that's the rule this bridge created. Wind tunnel testing became standard practice for every major suspension bridge built since. Not a law passed in one moment, a changed expectation an entire profession adopted because of what happened here. A bridge that fed its own motion until it tore itself apart taught engineers to test for exactly that, before building, not after. That's still how it's done.